So accommodation. We'll talk about accommodation in a second, but pretty much what accommodation is how your eyes adjust to what they're seeing. So in picture A here, we see what normal vision looks like, right? So you see the candle, the lens bends the light, um, so it adjusts slightly to deal with objects near and far away, and then it focuses on the retina in the back of your eye. Well, B, here we see nearsighted vision, right? So it's looking at the candle, but the rays are focused before the retina, right? So if you look at A, how it focuses at the back of the retina, on B, it focuses before the retina, so when they eventually get there, it's blurry, right? That's why people are nearsighted. Farsighted, it's the opposite. Rays focus past the retina, resulting in blurred vision. So you see how it focuses too far away. So whether you're nearsighted or farsighted, it's because the lens, it doesn't focus directly on the retina. Either it's too soon, right before the retina, that's people who are nearsighted, and farsighted, it focuses past the retina. So astigmatism. Right? A lot of times we hear this word, but we don't really know what it is. So astigmatism is when the cornea is slightly curved rather than completely round. So with astigmatism, light focuses on several points of the retina rather than just one point. This is what people with astigmatism versus without. All right, so if you see it on the left, that's what it looks like. On the right, if you don't have astigmatism. So like I grew up with astigmatism, and that's just how I like would drive at night, and that's how I saw. Once again, didn't realize that's what other people weren't seeing. I thought the lights were just like that. Vision, a couple vocab words like we talked about, right? Acuity we talked about earlier. That is clearness of vision, right? So acuity, we talked about visual acuity, where vision is best, is in the fovea because it only has cones. Accommodation is the ability of the eye to focus. That's what we just talked about, right? With nearsighted, it focuses before the retina. Farsighted, it focuses past the retina. Feature detection. This is just a process by which specialized nerve cells in the brain respond to specific features of a stimulus, such as lines, edges, angles, or movement. That's just a vocab word to make sure you know. And that's how we see, is because they're kind of predetermined to see lines, edges, all these different things, and they put it together to get the vision that you see. Parallel processing is the ability of the brain to simultaneously process incoming stimuli. So the brain divides what it sees into four components: color, motion, shape, and depth. So individually analyze, and then you compare it to stored memories. So the brain then combines these into one image that you see and comprehend. So we've talked about this before, right? There's so much stimuli coming into your brain. If they had to individually do each one, we wouldn't be able to process all that. Your brain's like the super computer. I know at one time they said everything your brain can do would be the size of like 2 city blocks. Now we have smaller computers, so maybe that would be smaller. But you just see how much the brain does. So what it does is parallel processing. It does things at the same time, right? So it's looking and it's processing all these things at the same time. And the main things they focus on when we talk about vision is color, motion, shape, and depth. It's looking at these four things, and then it compares to your stored memories, right? Things you've already seen in the past, and it recognizes, hey, I know what that is because it looks similar, it has a similar shape or motion or color or whatever it might be. And then your brain computes that to you, and you're like, oh, that's a chair, or that's a lion, or whatever it might be. Just, if you know what parallel lines, what that is, you should understand parallel processing, right? Your brain simultaneously processing that incoming stimuli. So a theory on how we see. It's called the Young and Helmholtz trichromatic theory, right? Tri, we all know what tri means, three. So it's also called the three color theory. This theory of color vision that says cones are tuned to be sensitive to red, green, and blue light. So if you remember the picture of the retina and we saw the cones at the bottom, we saw like red, green, and blue, right? All the colors we see are a combination of these three colors, right? So that's kind of makes sense, right? Trichromatic, three-color theory. Young and Helmholtz is the one who came up with it. Any of those names you might see. So it's similar to a design of a color TV, or at least how TVs used to be designed. I'm not sure how they are now with the HD and everything like that. But it used to all be based off the three colors. And so based off those three colors, they would create any color you would want. And so we're going to see how this theory works, and then why it doesn't necessarily work, what the criticisms are of it. So if you've ever seen like the old school like theaters, a lot of times they would have different colored glass that they would put over the lights. So they would use, that blue, the red, and the green to make all the different colors, right? So you notice all the different colors they make, and in the middle, white is the reflection of all colors. So the opponent processing theory of color vision. So some aspects of our color perception are difficult to explain by the trichromatic theory alone, right? And this is what I was talking about. So there's something called afterimages, and we'll see a bunch of afterimages right now. But that is one, criticism of it, because it doesn't explain why we see afterimages. So if we viewed color stimuli for an extended period of time, we'll see an afterimage in a complementary color when we view something white, right? So that's the afterimage. And pretty much what it's saying is the different colors are paired with something, right? So if you exhaust one color, you're going to see the opposite color. So the opponent processing theory says that color is processed in opponent pairs, right? So red goes with green, yellow goes with blue, black goes with white. So light that stimulated one half of the pair inhibits or hinders the other half. So if I stare at something that's red, I'm exhausting all my red cones, and if I blink or I look at something else, I'm going to see green, because that's what's paired with it. And so we're going to see a number of afterimages. And what you're going to do, there's going to be like a dot or something in the middle. You're going to stare at that dot for about 30 seconds. Try not to blink. And then I'm going to change the slide, and it's going to be a white slide, and you're going to see the after image of it. So here's the first one. So now just stare at that dot. All right, stare at that dot. I'm going to have you stare at it for about 30 seconds. Just relax your eyes and stare at the dot. What you're doing now, you're exhausting your cones, right? The green cones with the black and the yellow. And then when I turn the slide to the white slide, you're going to see the after image. So then you're going to see a red, white, and blue flag. Keep staring, a couple more seconds. Then I'm going to turn it to the white slide. Now, did you see a red, white, blue flag? Sometimes if you blink, it'll stay with it. It'll last a little bit longer. So that's pretty cool, right? So that's the after image that you see, because you exhausted all the cones and you saw the pairs, what it's paired with. And that's the opponent processing theory. So let's try another one. Keep staring at that one once again for about 30 seconds. I'll change it in about 30 seconds. This one's only black and white, so when I turn the page, right, the white part, you're going to see it as black, and then the black part will just be white. It'll just be the background. It'll go with the background. So keep staring. About another 10 seconds. Relax your eyes. Try not to blink. And as I turn the page to the next slide, you're going to see the after image. Remember, you can blink and it'll stay there. Now, what did you see? Did anyone see Jesus? Have a religious moment there, maybe? All right, so that is an after image. And so if you look online, and I'll try to post a couple of the ones from YouTube, but there's just tons of them on YouTube and online. So let's try one more. This one I'm not going to go from one slide to the next. And this one's a little bit harder, so you have to do this on your own. What you're going to do is you're going to stare at the bird for about 30 seconds. And after about 30 seconds, you're going to then stare at the cage and blink. And you're going to see like a black bird in the cage, because that's going to be the after image, the black and white, how it's paired together. So keep staring about another 10-15 seconds and try to put it in the cage. right, was anyone able to do it? So hopefully you could, but like I said, this one's a little bit harder to do because you're putting a bird into the cage, but a lot of students are able to do it. So explaining this whole afterimage effect, right? So in the retina and the thalamus are ganglion cells that we talked about before that are turned on by red but turned off by green and vice versa. So a single ganglion cell handles both, but only one at a time, right? So that's why we don't tend to see greenish red things. So it can only see red or green as it's staring at something. It can only use one part of that cone at a time. And so what happens is you tire out those receptors, right? So by tiring out the green receptors staring at the image, the other opponent red receptors are turned on when we view white, right? Because remember, white reflects all colors. So hopefully that's making sense to you, right? The opponent processing, how the red and blue, like the green and red are paired together, the black and white are paired together, right? And then the yellow and blue are paired together, right? And so if you exhaust one, then you see the other one. So what's our current view, right? So we talked about the two different theories. Well, our current view of color vision is that it's based on both the trichromatic and the opponent processing theories. Like a lot of things in psychology I've talked about, usually the modern theory is a combination of the two. So what we say now is color vision is a two-stage process. The retina's red, green, and blue cones respond in varying degrees to different colors, right? That's the trichromatic theory. And then their signals are then processed by ganglion cells that encode color in terms of opposing pairs while they're sending the information to the thalamus. Once again, thalamus processes all of your senses except for smell, and then on to the visual cortex, which also encode the information by opponent pairs, right? That's the opponent processing theory. So all you have to know, our current view is just a combination of both. That's it. All right. You got the trichromatic theory and then the opponent processing theory. And the last slide is just color constancy. This is something we've already talked about before when we talked about the different constancies, but it plays a part in vision as well. So color constancy, so this is just really a review, ensures that the perceived color of objects remains relatively constant under varying illumination conditions. So an example would be this, right? The colors of the hot air balloon are recognized as being the same in the sun and the shade. So you got two pictures here. So notice the bottom half, right? The hot air balloons in the sun, it looks like one color. The top half, it is in the shade, it looks like different colors, right? So color constancy says we know it still stays the same color. It didn't change colors. It's just in a different light, right? So sometimes it's called light constancy as well. So remember when we're doing our picture project, you have to take two pictures of the same thing in different color lights to show that it looks different, but yet we know it's still the same color.